right, up next is Mr. Quinn. He's going to tell us about grain yield following rye cover crop.
All right, so good afternoon. Thank you all for being here. So the basis of my project is centered around this idea that there's continued interest in and continued promotion of using a rye cover crop in Kentucky. And kind of the main ideas behind this is that one, rye is labeled as a workhorse cover crop. It basically grows anywhere in any conditions and produces a lot of biomass. Rye is also really effective in reducing soil erosion, which is important in Kentucky. It's effective in reducing nitrate leaching, resistant weed populations. It's also very good at improving water retention, which is good in the shallow soils that Kentucky has. It's also good at building up soil organic matter levels over time. But despite these proven benefits and the promotion of this cover crop, is when corn is planted following rye, it tends to have certain issues. It tends to result in oftentimes in yield loss. And this tends to deter a lot of producers from actually using this and capitalizing on the benefits of this cover crop. And certain issues that corn has is that one is reduced emergence or reduced seed to soil contact at planting. It has nitrogen immobilization issues, which is also often driven by the high seed to N ratio of the rye cover crop biomass. We also have seen increased seedling disease pressure in corn following rye, and also increases water and nutrient depletion and competition for that corn following that rye cover crop. So a lot of research has been done on these factors, but the main question is, how do we manage this? And we need to look at this and how can we manage so that producers aren't losing the yield, and two, that they can use this cover crop more than they already do. So the objective of my trial was to evaluate corn emergence, in-season growth, and grain yield response, multiple seeding rates, and an in-furrow starter combination of fertilizer and fungicide following a rye cover crop. And our hypothesis was that higher seeding rates and an in-furrow starter are required when following a rye cover crop in order to maximize that corn grain yield. So this study was performed just in one location this last year in Lexington, Kentucky. It was performed on a bluegrass Maury silt loam. Corn was no-tilled following soybean, and it was irrigated. What's unique about this trial is that we used a white corn hybrid, and this was due to there's a lot of popularity of using white corn hybrids in Kentucky. The white corn was seeded on May 3rd in 2018 in 30-inch rows, and then we harvested that corn on September 30th in 2018. We adjusted that grain yield to a 15.5% moisture. Experimental design was a randomized complete block factorial design. We utilized 10-foot wide by 30-foot long plots or 4-row corn plots. It was replicated 4 times through the field. We had 3 individual factors. So the first factor was fall seeded cereal rye. That was seeded at 60 pounds per acre. And then we had a in-furrow fertilizer and fungicide starter. So that was 10-34-0, which was applied at a rate of 5 pounds of N per acre. And that was tank mixed with an azoxystrobin fungicide or at 14 ounces per acre. Then the last factor was seeding rate. So we used 5 different corn seeding rates, and that ranged from 20,000 to 44,000 seeds per acre. Data collected throughout the year, we started with rye cover crop biomass, or total. We looked at total pounds of rye per acre, a CDN ratio, and total N removed, and that was strictly above ground biomass. We looked at pre-plant and pre-side dress inorganic N soil analysis. We did daily percent corn emergence as well as stand counts. We did plant and seedling disease monitoring. We looked at corn heights, plant greenness, and we used a SPAD meter to determine the plant greenness. We looked at R1 ear leaf tissue N content, R6 whole plant and grain N content, and we also looked at grain yield, test weight, and moisture. The data was analyzed in the Glimix, Reg, and NLIN procedures of SAS and an alpha value of 0.1. Treatment factors were considered fixed, and then replication was considered random. We utilize a quadratic plateau regression model in order to determine the agronomically optimum seeding rate, or what is that exact seeding rate required to maximize corn yield over different treatments. And if yield did not plateau in the regression analysis, the quadratic model instead of the quadratic regression model was used, and the AOSR was determined as the highest seeding rate examined. So we're not extrapolating beyond higher seeding rates. So this is some of the rye cover crop, the individual rye cover crop data from this past year. The fall seeded rye cover crop was terminated about 14 days prior to corn planting. And this rye cover crop in 2017 was had a very late planting, delayed planting due to significant rainfall in the fall. And due to that delayed fall seeding, we have very low amounts of biomass. So it only produced about 512 pounds per acre of total biomass. Had a seed to N ratio of about 16:1, which is actually below that threshold of about 24 to 26:1, where we'll typically see soil N immobilization. But even though that rye cover crop was small, it actually removed about 13 pounds of N per acre, and that's above ground biomass. And when we looked at soil pre-plant and pre-side dress inorganic N analysis, it was about 9 and 15% less in the corn plots that were following that rye cover crop. So this graph illustrates corn grain yield, which is on the y-axis response to the multiple seeding rates that were examined on the x-axis. The blue line indicates corn, that is the corn response when following rye and including an in-furrow starter. And then the orange line indicates corn response to seeding rate when not following rye, but is also including that in-furrow starter. And that blue number indicates the agronomically optimum seeding rate when corn is following rye, or that seeding rate required to maximize corn yield. It's actually at 44,000 because that this curve did not plateau. And the orange number indicates the agronomically optimum seeding rate for corn when not following rye, but also including that in-furrow starter. And this graph shows that when corn is following rye and including an in-furrow starter, we needed about 4,000 more seeds per acre, and it potentially was actually more. We needed more seeds per acre in order to maximize corn grain yield. And this goes against our original hypothesis that in-furrow starter would actually help with corn emergence. And what we'll see, and is what I'll talk into later, is that it actually tended to harm some of the emergence we saw this year. So to further expand on that, I also present this again as grain yield, corn grain yield response across the multiple seeding rates examined. Again, the blue line is corn following rye, and then the orange line is corn response when not following rye. And the difference in this data set is this is without the in-furrow starter. So without the in-furrow starter, the agronomically optimum seeding rates were basically the same. So that again goes back to the point that that in-furrow starter may have actually been harming the emergence. We actually saw much more delayed emergence with that in-furrow starter. So this table illustrates a rye by in-furrow starter plant growth and greenness interaction that we observed in 2018. This table shows that when corn is following a rye cover crop and includes an in-furrow starter, V4 and V12 plant height, as well as V6 and R1 SPAD values or plant greenness, was actually statistically similar to corn not following a rye cover crop. Whereas if you look at corn that's following a rye cover crop without that in-furrow starter, the V4 and V12 plant height, as well as V6 and R1 SPAD, were statistically less than all of the other treatments. So although we are seeing delayed emergence and emergence issues with that starter, it's also, based on this graph, it's also helping that plant growth as well. So without that starter, there is some stress going on, even with as little and small that cover crop was. And that in-furrow starter is tending to actually help that corn plant with some of that early season stress. So although we saw interactions with the agronomically optimum seeding rate, as well as plant growth and plant greenness interactions throughout the season, This graph or this table illustrates corn yield response to both rye cover crop and in-furrow starter across all factors examined. And with grain yield, we did not observe any significant interactions, so I'm just presenting the main effects. And there was no significant grain. This graph illustrates that there was no significant effect of a rye cover crop or an in-furrow starter on corn grain yield in 2018. And that's across all study treatments and all seeding rates. So preliminary conclusions is that within an in-furrow starter and following a rye cover crop, corn required a 10.4% increase in agronomically optimum seeding rate. We observed delayed emergence with that starter. And when we actually looked at a rye cover crop plus the in-furrow starter, we actually observed even more delayed emergence. And this will be a subject into the future that we'll actually look at more closely to try and understand this a little better. Without that in-furrow starter, corn agronomically optimum seeding rate did not differ between the preceding rye and no rye, which goes again to show that that in-furrow starter was giving us some issues when it comes to emergence early on. But even though we did see this delayed emergence and stand issues with the starter, the in-furrow starter showed the potential to alleviate certain corn stresses. So we observed smaller plants as well as less green plants following corn, and that tended to be alleviated with that in-furrow starter. But across all treatments, neither the rye cover crop nor in-furrow starter significantly affected grain yield. And this was likely due to the low biomass we had due to that delayed fall seeding. We had a low C to N ratio, so we don't expect any N immobilization occurred. We also had sufficient soil P levels, so we used a 10-30 furrow, so 34% phosphorus in-furrow starter fertilizer. So we don't suggest any response to that phosphorus fertilizer. We observed delayed emergence. We also observed improved plant growth in that corn. So whether or not those potentially may have equaled each other out and may have been the reason behind why we didn't see a grain yield response. So one thing we have learned with this trial over the last year is that further investigation into this actual rye cover crop and in-furrow starter interaction will be required. That leads me to future research and what we're doing over the next 2 years. So I'm going to have 2 more growing seasons. We actually have an earlier seeded cover crop. I actually terminated it yesterday and the rye cover crop was up to my knees. So it's much more biomass this year and we're hoping we get much even better results this coming year. We added 2 more locations. We added an on-farm location in Hardin County, which is a rain-fed location following soybean. So Lexington was irrigated. We also added another location in Princeton, which is rain-fed following corn. One thing about the trials in the future, or this year, starting this year, is that we changed the in-furrow fungicide. After talking to certain couple of the plant pathologists as well as farmers, the in-furrow fungicide, although it's labeled for in-furrow use that we use, seems to have some issues with emergence and can be kind of the reason of why we saw those delayed emergence and stand issues. So we're actually switching to an in-furrow fungicide that's actually marketed and promoted for in-furrow use in corn. We're also adding a complementary study to this. We're actually going to separate out this fertilizer and fungicide in-furrow treatments to actually look at those individually. We're actually going to start a laboratory corn root disease analysis. We'll actually plate corn roots in the lab and see what disease grows on those roots following rye. We'll actually look at different rye cover crop termination timings. So we'll look at rye terminated approximately 2 weeks prior to corn planting, but also terminated immediately after planting. We're actually going to look at using sensors to actually dive into more of the soil moisture and soil temperature differences between rye cover crop and no rye cover crop plots, so we can dive into more of those results and interactions that we saw. So that I'd like to thank first the Kentucky Corn Promotion Council who funds my research projects. I'd like to thank my advisors, Chad and Anna, my committee members as well, our research technicians, Julie and James, and then the amount of undergrad students and visiting scholars and other professors and research techs have helped greatly with this project. So with that, I'll thank you, and I can take any questions.
Anybody have any questions?
Fair. Offhand, I would say no. I think most of the treatments were, I guess we can go a little back and look at the graphs. Talking about just the spread in the grain yield. Over basically everything I've seen is that they were pretty equally variable. And one thing with the in-furrow starter is that a lot of times with starters, they suggest that it can decrease the yield variability. And that's something we just didn't see this year.
All right. Thank you very much for that. Next up is Jason Simmons, and he's going to be talking to us about poultry litter.
Microphone.
Good afternoon. Like you said, my name is Jason Simmons, and I've been working on my PhD part-time while working as a science technician for the Agricultural Research Service research unit in Bowling Green, Kentucky. And that's actually who funded this project under National Program 212. So poultry litter is used as a nutrient source in the western portion of Kentucky. It's traditionally surface broadcast, which could come to arise some issues with not having uniform application, some odors subject to residential areas, nearby residential areas, and they could also pose several environmental issues such as surface runoff, ammonia volatilization, and nitrous oxide emissions. So researchers at the USDA developed an implement that would subsurface ban poultry litter under the soil surface with minimal soil disturbance. You can get a precise application rate from the agitator breaking up the large pieces of cake in the poultry litter, and you can also adjust the conveyor and tractor speeds to get a uniform rate. However, they've noticed that the moisture content has to be sort of below 25% to get good results. And up to this date, there hasn't been any research on nitrous oxide emissions and ammonia volatilization when you adjust the lateral spacing of these subsurface bands. So the main objective of this project was to determine the impact of subsurface application of poultry litter in 1, 2, or 3 bands between the corn rows on nitrous oxide emissions and ammonia volatilization compared to the traditional surface broadcast of poultry litter. So the project was done down in Bowling Green at the Western Kentucky University Research Center, and it was a randomized complete block design with 6 treatments and 3 replications. The treatments included an untreated control that received no nitrogen, and that's UTC, a 32% UAN treatment that was surface banded, signified by FERT, F-E-R-T, and then a poultry litter surface broadcast, PLBR, and then also 3 subsurface band treatments, either PL sub 1, 2, or 3. And our target nitrogen rate was 180 kilograms of nitrogen per hectare. And we assumed 100% nitrogen availability from the poultry litter. And the pictures below just sort of give a quick overview of what the placement of the subsurface band treatments in relation to the corn rows. So basically, PL sub 1 is on 30-inch centers, PL sub 2 is on 20-inch centers, and PL sub 3 is on 10-inch centers. So for nitrous oxide emissions, we used static vented chambers, and we took samples at 0, 15, and 30 minutes after deployment of the chamber lids onto the anchors. And these spanned from row to row in the corn plots. And we had 24 sampling dates each in 2014 and 2015. For ammonia volatilization, we used a an acid trap open chamber. It's really just an altered 2-liter bottle with a foam strip as the acid trap. So to get into some of our results, the bottom graph shows our observed nitrous oxide emissions in micrograms nitrous oxide nitrogen per meter squared per hour. And on the x-axis, we have month of the year. And on the left, you have 2014. And on the right, 2015. And this graph is a little busy, so I just really want to point out a few things. The F's in both of the lower graphs represents when we applied our nitrogen treatments. And another thing to point out is most of the nitrous oxide emissions occurred within 45 days after treatment application. In the upper graphs shows daily and cumulative precipitation. Daily precipitation is the red bars in millimeters, and cumulative precipitation is the blue line in centimeters. And what's interesting to see is that these pulses of nitrous oxide in both years sort of occur around large rain events. So with these saturated soil environments, with the addition of available nitrates, could suggest that a potential source of this nitrous oxide was from denitrification. These graphs here show the cumulative N2O emissions on the y-axis in kilograms nitrogen per hectare for 2014 and 2015. 2014 on the left, 2015 on the right, and month of the year on the x-axis. And in 2014, the poultry litter subsurface banded treatments had lower nitrous oxide emissions compared to the poultry litter broadcast, which is the red line. In 2015, poultry litter subsurface 2-band was the only subsurface banded treatment that had lower nitrous oxide emissions compared to the poultry litter broadcast. And also in 2015, the poultry litter subsurface banded 2 bands was also similar to that of the untreated control, the no nitrogen check. So as far as total nitrogen conservation, the values were really small compared to our total nitrogen application rate, which was 180 kilograms of nitrogen. So it was only 0.25% of the nitrogen applied, which has a very small economic impact. However, it can have a very large environmental impact. So nitrous oxide has a 298 times greater global warming potential than carbon dioxide. So with the amount of nitrous oxide nitrogen that we conserved from subsurface banding poultry litter, this was equivalent to 213 kilograms of carbon dioxide. This equates to 840 kilometers driven by a passenger car, 90 liters of fuel consumed, and 105 kilograms of coal burned, or operating a 150 horsepower tractor for 3.2 hours. And this is just for one hectare. So moving on to ammonia volatilization, the upper 2 graphs show the observed ammonia volatilization at our sampling dates in kilograms nitrogen per hectare. And I just want to point out, both in 2014 and 2015, the majority of the ammonia loss occurred within 30 days after treatment application. And the bottom 2 figures has the cumulative ammonia volatilization in kilograms nitrogen per hectare. And then on the x-axis is days after application. And in both 2014 and 2015, poultry litter subsurface banded treatments had lower ammonia volatilization compared to the poultry litter broadcast and the fertilizer UAN treatment. And they were also equivalent to that of the untreated control, the check. And we also did not notice any differences between either 1, 2, or 3 subsurface bands of poultry litter. So in summary, for nitrous oxide emissions, nitrous oxide flux pulses coincided with rainfall events. In 2014, poultry litter subsurface band treatments had reduced nitrous oxide emissions compared to the poultry litter broadcast. And in 2015, only poultry litter subsurface 2 bands between the corn rows had significantly lower nitrous oxide than poultry litter broadcast, and also that of the fertilizer UAN treatment. And we observed no difference between the poultry litter subsurface band treatments, whether it be 1, 2, or 3 bands between the corn rows in both years. For ammonia volatilization, poultry litter subsurface banded treatments were statistically lower than that of the poultry litter broadcast and the fertilizer UAN treatments. And they were also similar to that of the no nitrogen untreated control. We also didn't observe any differences between putting the subsurface bands in 1, 2, or 3 between the corn rows. So should farmers adopt this technology over PLBR? We did prevent a loss of nitrogen as ammonia. The max we saw was 1.8% of the total nitrogen applied. We also saw a reduction in nitrous oxide emissions, a max of 0.45% of the total nitrogen applied, which this is rather small and as far as an economic hardship for the farmer, but like I showed earlier, it may have a greater impact on the environment. And in our case, in this scenario, we didn't see a difference in banding the poultry litter in 1, 2, or 3 bands, but farmers and then the developers of this implement will need to consider that when they look at equipment costs. So as the frequency of the bands increase, so does the cost of the implement. So thank you. I'll take any questions.
So on your graph where you showed cumulative nitrous emissions, it looked like 2 bands was lower than 1 band or 3 bands.
Yes.
That seems a little bit counterintuitive, doesn't it? How do you explain that?
Then 1 or 3?
Yeah, because I mean, you would think that. Like, why? What's the reason?
Well, it could be splitting that poultry litter rate into 2 bands from the 1, but also being closer in proximity to the corn rows. Like the 2 bands was only 10 inches from each, but the 3 band, had 2 of them that were close to the corn rows. However, 1 was just sort of in the middle, a little bit further away from the corn rows. So that could be an explanation for the increase from the 3 band. We did PL sub 2 did have greater corn yields than the other 2 subsurface banded treatments. It had greater yields. Yeah, we do have all that information. I just didn't know if I'd have time to go over it today. Yeah, that would definitely play into the I guess the financial and the fuel cost. excuse me, we do have gravimetric water content for the soil samples, and we also had some soil moisture sensors inserted into only one replication of the project. Yeah, so.
All right, thank you very much. Appreciate it. Next up, we got Mr. Huang, who's going to talk about soil organic response.
Good afternoon, everyone. The topic I'm going to talk today is simulated soil organic carbon responses to long-term no tillage and climate change in Kentucky. I'm going to talk about my presentation in 5 parts. To begin with, I'd like to make a brief introduction of my research background. As we all know, soil organic carbon is a key indicator of soil quality and soil health. It plays a significant role in providing ecosystem services, such as preventing soil erosion, increasing soil water retention, and soil fertility and biodiversity. And there's an urgent need to increase soil organic carbon to address the challenges of climate change, food security. It is suggested that if the soil carbon levels was increased by 4 per million per year, the annual increase in atmospheric carbon dioxide would be stopped. And since then, in recent decades, many strategies have been taken to meet the goal of increasing soil organic carbon. And one of the most popular management in agriculture system is no tillage. And we have conducted a meta-analysis to analyze the impacts of no tillage on SOC and greenhouse gas emissions as compared with conventional tillage, using more than 2,000 data pairs from published papers. And on average, we found that no tillage can increase soil organic carbon by 8% compared to conventional tillage. And it also decreases carbon dioxide and green methane emissions, although the nitrous oxide emission can be enhanced under no tillage. And we also found that the benefits of no tillage are dependent on the interactions of no tillage with climate, soil conditions, and other management practices such as cover crops. And so in this study, our goal is to further investigate these interactions using an integrated model approach. The objectives of this study is to first improve an agro-ecosystem model to simulate different tillage impacts. And second, evaluate the improved model and examine soil organic carbon dynamics in a long-term no tillage system. And third, identify the relative contributions of different driving factors such as temperature, precipitation, atmospheric carbon dioxide, and nitrogen deposition to the changes of soil organic carbon. The model we use is the dynamic land ecosystem agriculture, which can simulate the carbon, water, and nutrient cycles in agro-ecosystem. This model has been widely used to investigate the responses of different pools and fluxes that respond to climate change and land use change and land management. The carbon dynamics in the DLEM-Ag tillage module, you can see as in this framework. Generally, plants acquired atmospheric carbon through photosynthesis, and the fixed carbon enters soil mainly in the form of above ground and below ground plant biomass. And carbon loss from the soil mainly through soil respiration, surface runoff, and leaching. And this is the conceptual model we constructed to simulate the impacts of tillage. And we consider tillage in combination with residual management. As we know, tillage mainly disturbs soil through its mixing residues and within the tilling depth. And the mulching effect of the residues would further influence the soil water dynamics and associated biogeochemical processes. And the mixing effects of tillage will also directly influence the hydraulic conductivity of soil, and also will accelerate decomposition rate. To evaluate the improved model, we have collected data from a long-term tillage site. The Blevins long-term tillage trial has been established in 1970. It is one of the earliest studies to conduct tillage impacts. It has a continuous corn with a winter cover crop system, and the major treatment includes no tillage versus multiple plow with 4 nitrogen rates. And during the past 50 years, there has been continuous observation on soil organic carbon and crop yield, and also study to collect greenhouse gas emissions from last growing season. To drive the model, we also need the climate information at this site. As we can see from this figure, we can see that both the mean annual temperature and total precipitation has a slight increasing trend during the past half century. And along with elevation in atmospheric carbon dioxide concentration, the nitrogen deposition has an annual variation, but no obvious changing trend. We then run the model through, from 1970 to 2008, and we compare our simulated results with the observational results. The X represent the observed value, and the Y-axis represent the simulated values. From this result, we can see that our model can well predict, can well match the observational data against crop yield and soil organic carbon. And our simulated carbon dioxide are also well located in the standard deviations of the observed carbon dioxide fluxes. And our model results also suggest that there was a great carbon dioxide emission during the initial of the experiment of the growing season. But we haven't got the opportunity to find that support from the observed carbon dioxide emission. This result from this simulated result probably because that the high carbon dioxide emission at the beginning of the growing season might caused by the faster decompose of the fresh cover crop biomass. And our model also shows that can well catch the overall trend of the change in annual soil organic carbon. For no tillage and for both tillage system, there was a slightly decreasing trend at the initial years, and then in no tillage system, also soil organic carbon started to increase, and in tillage system, the soil organic carbon keep slightly decrease. And we have found from the previous study, it said that during the previous first 10 decades of the experiment, there was a very poor stand of cover crops. We assume part of the decrease in soil organic carbon might be the lower input from cover crop. To further analyze the difference between the soil organic carbon in both tuning systems, we further check the carbon balance in different systems. As we mentioned before, the major input to soil organic carbon are lithophil carbon and corn residues and cover crop biomass. And the carbon loss from the soil mainly through soil respiration and soil erosion and leaching dissolved organic carbon. In the upper figure, we can see that corn residues is the main contribute the most to is the main carbon source, and soil respiration was the main carbon, the main way that carbon lost from the soil. And this picture shows that the lower picture shows the difference between tillage system and no tillage system. As we see in no tillage system, it has a relative higher carbon input, but has a relative lower carbon output. This resulted in the net increase in soil organic carbon in no tillage system compared with tillage system. We then conducted 6 single factor simulation to analyze the contribution of each driving factor. We find that carbon dioxide fertilization and temperature change during the past decades have a positive contribution to soil organic carbon sequestration. And precipitation has a negative effect on soil organic carbon. And since this is we simulate the results in a nitrogen unlimited system, the nitrogen deposition effect is negligible. And tillage is the contribute the largest decrease in soil organic carbon. To sum up, and first, we found that this improved DLEM-Ag model can well simulate the impacts of tillage and no tillage on the carbon dynamics. And no tillage could benefit soil organic carbon largely due to higher carbon input and lower carbon dioxide emission compared with conventional tillage. And increasing atmospheric carbon dioxide concentration and temperature could enhance soil carbon sequestration through promoting plant growth, and while precipitation will reduce soil organic carbon during this study period. And no tillage system seems to have a more resilience to climate change than conventional tillage in the study area. Although our model can well capture the main trend, there are some uncertainties in this in the current model, and we will need more information to initialize and calibrate and validate the model. For example, we might need information regarding the planting day and harvest day to simulate the phenolic pattern, and also the biomass of cover crop at termination to simulate how many biomass that was come from cover crop. And for our future study, we'll also need to explore how soil organic carbon will respond to climate change in the future. With that, I would like to acknowledge everyone that has helped me in these projects.